This section deals with the uses and abuses of percents. What we mean by that is sometimes we hear percentages and we'll put a little too much faith in them, or we'll have somebody who does some fast talking and actually do some manipulation of percents that you're just not allowed to do. The first thing we're going to talk about is how percentages can kind of lie to us. And the way that happens is a phenomenon known as Simpson's paradox. Now the definition, I'll read it now, but it's not going to make as much sense until we actually see it in action. But something appears to perform better in each of two or more group comparisons, but actually performs worse overall. Let's talk about this chart. This chart has a lot of things going on. Apparently I have an acne treatment. I have an old one and a new one, and I gave it to some people to see how well it dealt with their acne. Well, I categorized my people as those who had mild acne and those who had severe acne. What I want to do is I want to find the cure rates for both treatments. We're going to start by looking at the people who had mild acne. We want to find the cure rates. Rates are going to be found in percentages. So, if I look just at the people who had mild acne, what was the cure rate for the old treatment? Well, the old treatment, 2 people were cured. But how many people got the old treatment? Not 8. There were 2 who were cured, 8 who were not cured. So 10 people took the old treatment. 2 divided by 10 changed to a percentage is 20%. So how many people were cured with the new treatment? Well, 30 people were cured, but 30 people out of how many? 30 cured, 60 not. That makes a total of 90 people who received the new treatment. So 30 divided by 90 is a third, which is 33.3%. If I had to go for the people who just had mild acne, it certainly appears that the new treatment worked better. What if now I focus my attention just on the people who had severe acne? With the old treatment, 40 people were cured out of 40 cured plus 40 not cured makes a total of 80 people. That's a 50% cure rate. With the new treatment, 12 people were cured out of 20. So 12 out of 20 cured, I think that's 60. Yeah, that's 60%. So if I look at the people who have severe acne, again, it appears the new treatment worked better, 60% versus 50%. But here's where strange things happen. What if I totally ignore whether there was severe or mild acne? What if I just looked at all the people who took the old treatment? If I do that, I have 2 plus 40, 42 who were cured out of how many people took the old treatment? I have to add them all up. So 40 plus 40 is 80, plus 8 and 2 is 10 more. 42 out of 90 people were cured with the old treatment. So if I change that to a percentage, that's 46.7% were cured with the old treatment. So let's look at the new treatment. The new treatment, 30 were cured and 12 were cured. That's another 42. But how many people total took the new treatment. 20, 90, 110. So 42 people were cured again, but this time it's out of 110 people. That's only 38.2%. So if I ignore whether somebody had mild or severe acne, it's the old treatment that worked best overall. So let's repeat what we said on the first slide. Simpson paradox occurs when something appears to perform better in two or more groups. So for mild acne, the new treatment worked better. For severe acne, the new treatment worked better. But when you look at the overall standings, it's really the old treatment that performed better. Well, how does that work? Because it's not a trick. And what we have to do is, let me get rid of some of these marks on our chart. Let's look again at our numbers. If I look just at the mild acne people for a minute, the old treatment, only 10 people took the old treatment versus 90 people took the new treatment. Well, what does that mean? How do I compare 10 people to 90 people? Unless I change it to percentages, I really can't. But if I'm one of these people who took the old treatment, what my results are, whether they're good or bad, they're going to count 10%. Each person is going to contribute 10% to what the overall results are. But what if I'm one of the 90? If I'm one of the 90, what happens to me is only going to, it's going to be a little bit more than 1% is how much my results are going to count. So if I'm in this group, my results are going to count for 10% good or bad. If I'm in this group, my results are only going to count 1%. Well, what if I look over here at the severe acne people? 80 got the old treatment, 20 got the new treatment. Well, these are only going to count 5%. Their results only count 5% toward the end. And again, these are going to be a little bit more than 1%. Those percentages are a little bit closer, but they're still kind of skewed. Now, what happens when we look overall? Overall, in one group we had 90 for the old treatment, and we had 110 for the new. These sample sizes are not the same amount, but they are a lot closer. These people are going to count a little bit more than 1%. These are going to count a little bit less, but it's not 4 or 5 or 10 times the amount. So it's the overall results in this case that are actually the most telling. Sometimes we don't have to work that hard. If you're given the percentages already, just say thank you very much and move on. If I look at the first half and I look at the percentages, Shaq did better in the first half. If I look at the second half, Shaq did better in the second half. But the real reason that I included this chart is because of who performed better overall. I don't want you to take one example and sort of get locked into a ritual that's not necessarily correct. In this case, I want to know who performed better overall. Okay, so if I examine Shaq's record, overall, he made 7 baskets. But how many times did he shoot? Well, he only shot 14 times. I don't add the 4 and the 3 and the 10 and the 4. He shot 10 times and he made 4 baskets. He shot 4 times and he made 3 baskets. So I'm only doing 7 out of 14. He made 50% of his baskets. So using that two-way table, I didn't want you to think that you didn't have to think about what you add up to do the overall. If I want to find Vince's percentage, he made 8 baskets. But he made 8 baskets out of 14, which is going to be more than 7 out of 14, but I'll get that percentage is 57.1%. So Vince did better overall. But when it comes to the overall, don't get lulled into thinking you always do it one way. You have to think about what your sample size is based on the problem. Now, another way people can mess with us with percents is by shifting their reference value. Because of losses, your employer asks you if you'll please take a 10% pay cut, and then in 6 months they'll give you a 10% pay raise, and the question is, will you be restored to your original salary? Well, it's more than just a yes or no question, because we really want to know if the answer is no, how much are you getting, more or less? So we could do this just with percentages, but we have to be careful. We have 3 different time periods. We start out, my original salary is 100% of my salary. Now, because that's my salary, let's just leave it as 100 so I don't get confused. Now, if I agree to a temporary pay cut, 10% pay cut, for the next 6 months, a pay cut means 100% of my salary minus 10% means I'm only going to make 90% of my salary. 90% as a decimal is 0.90. I'm going to multiply my 100 by 0.90. That's what will happen for the first 6 months. The second 6 months, I'm supposed to get a 10% pay raise. I don't start from the 0.90. A pay raise means I take all that I've got and I'm going to add 10%. And if I change that to a decimal, that's 1.10. Now, if I multiply those 3 numbers together, that'll tell me where I end up. That multiplies to 99%. If I started with 100%, I'm going to end up with 99%. So what that says is after 6 months, I'm going to be making 1% less than I did before. Let's try it again, but this time with a different scenario. I got a bad stockbroker apparently because he lost 60% of my investment during the first year. But then the second year, my investment increased by 75%. But he's trying to tell me that I'm now 15% ahead because I went down by 60 and then went up by 75. Well, I start with 100% of my investment. If my investment fell by 60%, that means I only had 40% of my investment left. So I have to multiply this by 0.4. Now, I do get a 75% increase, but that's afterward. So 75% increase is 175% as a decimal is 1.75. What does that leave me with? 70. So I started with 100%, now I'm left with 70%. That means I am 30% behind, not ahead, because he's a bad stockbroker. This is another example of shifting reference values. 60% of the people in my class are women, 80% of the women are married. Does that mean 48% of the people are married women? I like doing this, I call it my little chain rule here. Start with the big group. The night class is the large group, so I have the whole class. Now, if I take 60% of this group, that leads me to a bubble full of just women. So that's the first sentence. 60% of the night class are women. Now, what matters is what do I do with that last bubble? 80% of who? The women. So if I draw that, that's 80% coming off the woman bubble to get to the married bubble. So the only people in here are married, but since it comes off the women, the only people in here are also women. So that does mean that 48% of my night class are married women. 60%, 80%, if you do it on your calculator, 60% times 0.8 will give you 48%. So let's see what doesn't work. 70% of the school students are freshmen. So the big group is the students. Big bubble is all the students. And it's when I take 70% of them that I end up with a bubble full of freshmen. Now, where does my third bubble go? This is 10% of who? Not the freshmen, 10% of the students are carpoolers. Well, does that tell me how many freshmen are in the carpool bubble? No, because I took the carpool bubble from all the students. So anybody could be in that bubble. So there's nothing I can do with the 70% and the 10%. I'm not allowed to do that math. If I wanted to talk about freshmen who carpool, I had to have come off of here, but that's not what happened. So that's where that chain rule breaks down.